imagine instead of trying to make hydrogen, you could actually try and make other chemicals that are of interest, like ethylene or ethanol or even methanol. And you could do that using waste CO2, for example, from a point source. So I know a lot of you industrialists are probably interested to know, is this really economically viable? So we did a very simple analysis in a recent review paper. So what we've got here is a market price of many different products you can make from CO2 reduction as a function of the energy content. So the size of the dots represents the production of these different chemicals. What you've got here is that the cost of these chemicals, if you had a complete 100% thermodynamic efficiency using solar power. So we put that here, solar power at the standard price, which is $50 per megawatt hour. And we've also put the line for 20 megawatt hours. So that's for what they project, what people are projecting could be the future costs of solar panels. And the intercept, the y-axis, is the cost of CO2 captured from point sources. So no, actually, if you're looking at CO2 from air, the cost would be about 10 times higher. So the intercept would be up here. What's interesting to note is actually something like formic acid is a very, very small market, so not that much is produced. But actually, even if you're working really, really low efficiency, you could actually, the price is so high relative to the cost of electricity that it's really worth making it using electrosynthesis. However, if you look at something like methane from natural gas is very cheap. Using current technologies, it wouldn't really be worth trying to make methane right now, even though the market's very big. So another chemical that's actually really interesting is right now is you can only make ethylene from hydrocracking hydrocarbons. But actually, the economic case for making ethylene using CO2 reduction is not actually that bad. As long as you get quite an efficient catalyst, it could be worth making ethylene using a CO2 reduction. So if you're doing CO2 reduction, what you really want for that ideal catalyst is to have a very limited potential losses. So this is what the current would look at. So you have this is the thermodynamic potential. This is actually the current of what you'd want in an ideal catalyst. However, if you look at the most studied catalyst, polycrystalline copper, you can see there's huge potential losses over potentials, around 1 volt. And that's not even half the problem. It's not even 1/16 of the problem, because actually you have many, many, many different products being formed at the same time. So you have, so actually measuring this is a bit of a pain. So you need to do both electrochemical measurements. You need to do at least 2 analytical methods, including gas chromatography, NMR, liquid chromatography, or maybe mass spectrometry. So I've shown the data for copper. So all other metals only produce either CO, formate, or hydrogen. So what I really want is to make more energy-dense products. CO is okay, but it would be even better if we could make something like ethylene, like I mentioned earlier. So to try and understand actually why the CO2 is so inefficient, even on copper, which is the best materials, here we've got the DFT calculations from the group of Jens Nerskov and Karen Chan. So here's the free energy diagram showing barriers. This is at 0 volts, so essentially no bias. And then this is at a minus 0.5 volts. You need to drive the reaction quite far to actually decrease this barriers considerably enough to get a reasonable or measurable current density. So what you can see is actually there's one step in particular which is really, really uphill. Let's go from CO to CHO. And there's a very big barrier between the steps. So you can imagine maybe the ideal way of actually catalyzing reaction better would be to completely flatten this curve. Then you'd be able to operate with minimal potential losses. However, it turns out, so you can imagine you'd want to stabilize these transition states and maybe stabilize some of these intermediate states as well. However, it turns out you can't actually do that because there's a problem. So all of these intermediates all bind by the carbon atom. And it turns out that their stability scales linearly with each other. The key bottleneck, as I mentioned, is going from CO to CHO. There's linear scaling between binding energies and of the different intermediates and transition states. So ideally, if you wanted to have really, really high activity and low potential losses, you want a catalyst to be here, but all pure metals fall on this curve. So we call this a linear scaling relation. So copper is closest to this red area, the high activity, but still not good enough. So in collaboration with Jens Neskov, who was at Stanford at the time, he had the idea that maybe if you, according to DFT calculations, if you looked at bimetallic catalysts, you could break these scaling relations and actually get much higher activity than the pure metals. So we actually tried this out. We looked at gold cadmium catalysts, was supposed to be right at the sweet spot here. Whatever we did, actually, what we found, the reaction rates were a lot lower than gold. So this is a really big disappointment to us when we were measuring the amount of CO being produced. So what we think is actually we're not able to realize this idealized structure here. This is exactly what we found as well when we're looking at other bimetallic systems. For example, we put copper monolayer on platinum. Here we were observing it using electrochemical STM. As soon as we put CO2 there, CO2 produces CO, and CO pushes the copper aside, you form islands and expose platinum. So we really observe directly that the catalyst restructures a lot under reaction conditions. It's something to bear in mind when you're looking at these multi-component catalysts. So one way of actually getting around this constraint is to look at what we call a tandem device. So you'd have one electrode for CO evolution, another electrode for further reduction of CO. So actually, it turns out for CO evolution, this is a summary of many different studies in the literature. What you can find actually, you can actually get quite reasonable current densities, quite close to thermodynamic potential, which is about minus 0.11 volts. So you can actually make CO quite efficiently. So the next question is, how can we reduce CO further? So there's been some very interesting work from Matt Cannon. What he found is if you took a polycrystalline foil and oxidized it, then reduced it, we found he made what he called oxide-derived copper, which had a very high surface area, kind of a skeletal structure or foam of copper. What I found is instead of making, if you put that into a very alkaline electrolyte, you found that you'd make ethanol. So an ethanol is a much more desirable product than methane, which the polycrystalline copper normally makes. Also, the potential loss is a lot lower on this surface, mainly because we're looking at alkaline systems rather than a neutral solution where you'd normally test polycrystalline copper. So we were very interested in this. So actually, but we're very interested to know what is the active site on this oxide-derived copper. Why has it got lower selectivity to hydrogen evolution than polycrystalline copper? And why does it make a lot more ethanol than polycrystalline copper? So we sent a PhD student out to Stanford to actually, Matt Cannon's group, to actually probe this, Arnau Verdago, Casadevall. And what he found is actually by changing the annealing treatment, you can actually change the product distribution quite considerably. You could also change the roughness factor. The roughness factor didn't always correlate very strongly to the annealing treatment. If you look at the electron microscopy of these catalysts, you could see they're actually very rough surfaces. It's a bit difficult to actually figure out what is the actual active site on these surfaces that are responsible for the enhanced ethanol production. So at my former group, we had a lot of UHV chambers, and we had some nice methods of probing surfaces of materials. So one of our favorite methods was what's called temperature programmed desorption of CO. Essentially, what you do there is you absorb CO at very low temperatures in vacuum, and then you measure the temperature that CO comes off. So it doesn't dissociate, it just comes on and then comes off. So here's a temperature programmed CO on the copper single crystals, both on the terrace copper, so copper 111. We have very coordinated sites, or a copper step, which just have a lot of undercoordinated sites. So we then did the same kind of method to a polycrystalline copper. We saw, the CO essentially desorbs lower temperatures on the more coordinated sites, and then the more undercoordinated sites, which tend to be a bit more reactive, it absorbs at higher temperatures. So then we actually did it on the oxide-derived copper. We found it very, very interestingly, actually, we saw some very strongly bound CO corresponding to the CO that dissolved at very high temperature, which we didn't observe actually on the polycrystalline copper. And we actually, by changing the annealing treatment, we saw more of this high temperature shoulder. Actually, by modeling, simulating these data, what we found is actually percentage of these strong binding sites correlated very strongly to the CO reduction activity. So what we think is that some very strong binding site that's unique to this oxide-derived copper, and this is what's resulting in the ethanol formation. Even so, we still don't know exactly what the actual active site is at this catalyst, but there's something for future studies. So all the data I've been showing you so far have all been based on electrodes submerged in liquid electrolytes, whereas in a real device, what you have is an electrolyte is exposed to a gas phase. And you can get a lot higher current densities. And there's been really interesting work over the past couple of years, both from the groups of Sargent and also from Paul Kennis, to try and probe this. And now at Imperial College, we want to actually also operate in these high current densities. One of my PhD students, Rose Oates, in collaboration with my colleague Anthony Kuchanak, is using a method called the floating electrode method to actually probe the reaction and the accelerated mass transfer. It's something very interesting looking at now. So the other thing, so far I've been looking at kind of surface effects, so changing the surface to probe, to accelerate reactions. Another way you can do it is actually looking at dynamic effects. So we've got, at my former institution, my colleagues developed a very novel electrochemical mass spectrometry technique. I'm very excited because we're actually going to get one of these at Imperial College. What you can essentially do is measure gases with really, really high sensitivity, so picomole per second sensitivity. What we found actually was when we put oxygen, we did it by mistake initially, before we carried out the reaction, we could selectively favor methane production just for a few seconds over ethylene production. By changing the potential at which we absorbed oxygen, we could change the amount of this methane you see at the beginning of the transit. So if we didn't add oxygen at the beginning of the transit, this curve was completely flat. The steady state activity is the same as the initial activity. So this is a very interesting phenomenon. I think that there's more scope for actually tailoring electrocatalytic reactions dynamically. We can only really measure these reactions in the dynamic state by virtue of the very, very high time resolution and sensitivity of this new mass spectrometry method. So I'm coming to the end of my talk about CO2 reduction. I still have a little bit more to talk about hydrogen peroxide if I have just a couple of slides. But in summary, there's been huge progress made over the past 10 years. On oxide-derived copper, we found it was one of the most promising catalysts. We found an unknown but very strong binding site can enhance CO reduction to ethanol. To really go even further, we need to break the scaling between reaction intermediates. So we need to break this linear scaling. One effect that might be able to do that is actually to tailor reaction dynamically. There's something I want to explore in more detail. Finally, I'd like to go very, very quickly to hydrogen peroxide production, if I may. So if you talk to most electrochemists, they will say that when you're reducing oxygen, for example, in a fuel cell, hydrogen peroxide is the last thing you want to make. However, it's a really valuable chemical. This usage is increasing a lot, mainly as an environmentally benign oxidizing agent. Right now, it's made only about using the anthraquinone process in very centralized facilities. There's only about 50 or 60 plants in the world. And it's actually very, very challenging to transport hydrogen peroxide. So there's been a few very well documented accidents where hydrogen peroxide canisters have caught fire. However, for most applications, for example, wastewater treatment, you just need really low amounts of hydrogen peroxide, so very trace amounts, below 0.1%. So it turns out actually, you can actually make hydrogen peroxide using electrochemistry. And if you could do it in this kind of configuration I've shown here, you can make it on site. You only need water, air, and electricity. You avoid reacting hydrogen and oxygen directly. It's a continuous flow process. And now to get hydrogen peroxide exactly the concentration you want in pure water. However, what you need a catalyst that's able to steer the reaction towards hydrogen peroxide, not the more thermodynamically stable product, which is water. So we're looking at the literature actually. What we found is actually what people are doing is making things like palladium gold catalysts, or even using cobalt porphyrins. The problem is that cobalt porphyrins are not stable and palladium gold is not particularly active. But what was interesting about them, they always have isolated, very reactive atoms surrounded by more inert substrates. So in the case of palladium gold, they have an isolated palladium surrounded by gold. So we had the idea, let's look for an alternative to palladium gold. So the problem is when we're looking at the catalysts that people have already reported, they're not very active. So we actually had the idea, why not try using mercury instead to isolate the platinum atoms? So we tested that out. So it's actually very easy. You simply electrodeposit mercury onto platinum, and we tested it. We found that actually the activity was orders of magnitude better than the prior state of the art. We thought this is really great. Let's try and commercialize it. So as soon as we spoke to industrialists, they were a bit negative about the use of mercury, especially because people generally trying to phase out mercury. But they were very positive about this. Just the fact that we've shown that it's able to make hydrogen peroxide at very, very high efficiency. So it gave us inspiration to think we could actually look for other catalysts that don't contain mercury and actually make hydrogen peroxide on site. So we thought this is such a good idea. We actually set up a spin-off company, HP Now. Now it employs 12 people, and we're actually making hydrogen peroxide in commercial units, which we're selling on site. We've also teamed up with the big hydrogen peroxide producer Evonik to actually make it. This is actually a photo of hydrogen peroxide, one of our producing units being tested in the field. So now I've come to the end of my talk. I'm sorry, I'm a little bit over time, but not too bad, I guess. So my general conclusions, oxygen evolution is really, really important for many production of many different energy-dense products. It's an ideal source of protons. The big problem is you need more active catalysts, you need more stable catalysts. CO2 reduction can produce energy-dense chemical building blocks. There's been a huge progress made. There's still some more scope before it can really be industrialized, but it looks very promising. We actually, hydrogen peroxide synthesis is possible using electrochemistry with high efficiency. We set up a spin-off company to commercialize it. The more important take-home message is I think that electrochemistry has the potential to make many of our most coveted chemicals. So if you'd like to find out more about the future of electrochemical synthesis of chemicals, I suggest you look at this report. This is based on a workshop run by EnergyX back in July. I chaired the session on nitrogen reduction to ammonia, or co-chaired it. A topic I haven't been talking about today, but it's something I'm very interested in looking at in more detail. So this workshop is essentially in anticipation of a €1 billion flagship program from the European Commission. What we try to do is to define what would be interesting research to really make an impact, would really make breakthroughs to enable the increase in renewable energy in the future. So I strongly recommend you have a look at this report. So I'd like to thank all my collaborators, especially at the Technical University of Denmark, for many years of very exciting science, in particular Rasmus Frudendal, Stefano Mezzavilla, Lisa Pauli, Arnaud Verdagoa, Jarko Jovanov, Erland Berthausen, Claudia Roy, Søren Scott, and Daniel Trimarco, and also the director of our center, Ib Kirkendorf, also Peter Vesburg and Brian Siegel. They all contributed to the work I showed today. Also, I'd like to thank my external collaborators, Jan Rossmeisel, Maria Escudero, Yang Shao Horn, Reshma Rao, and Matt Kanan and Samira Sharastami, and obviously the funding bodies. Finally, I'd like to thank my group at Imperial College. Here's a photo of them having dinner at my home. So they're not only good at wining and dining, they're also really excellent scientists. And as I mentioned, we're setting up the lab right now, and we're making excellent progress. I'm looking forward to presenting some of their results in the near future. And finally, I'd like to thank you for listening. I'd be delighted to answer any questions.